Alright, we're going to continue section 15.3 in this video. We're going to start with an example. So example, find the work done by the force f of xy equals 2x plus y comma x in moving an object from 1, 1 to 4, 3. Alright, so one thing that you'll see in some problems is that notice we aren't even given a path along which we're traveling in this vector field. We just know our start point and our end point. So that's a clue that you know you're going to be using the fundamental theorem of line integrals because we don't even have a path to parameterize. Now, we could assume we were traveling along a line, but there's nothing in here that says we were traveling from whatever along this line from 1, 1 to 4, 3, or we're traveling along some curve that looks like this from 1, 1 to 4, 3. It could be either one. We don't know which one. But that's the whole point of independent of path, is that whichever path we're traveling, the amount of work done by this force is going to be the exact same. So first, to check to see if we are indeed independent of path, even though we weren't given a path at all, we do need to first look at the curl of f. So this thing is defined everywhere and its partials are continuous. So these four things that we talked about at the end of the last video, those are all equivalent to one another. So we're going to do this to make sure that this is the case, that 2 is the case, and then from there we can use the fundamental theorem of line integrals. So first, let's compute the curl of f. And see, do we get the 0 vector? So we have 2x plus y, and then x 0, ij and k, partial with respect to x, partial with respect to y, partial with respect to z. All right, this is equal to, so notice, I think we've done one of these before, is that when you have a vector field in R2, then, or in 2 dimensions, excuse me, then what you have is when you look at the I, when you look at their I component, you're going to end up with a partial with respect to y of 0 minus a partial with respect to z of something that has no z's in it. So you're going to end up with 0. So 0 minus 0. That will always be the case when you're looking at a 2-dimensional vector. That's going to be 0 plus, then with respect to j, so that's minus, sorry. I'm just going to switch my sign, but minus. The j component, excuse me, not with respect to j. So we ignore this column. Partial of 0 with respect to x minus the partial of something with respect to z that has no z's in it. So we're going to get 0 minus 0 there. Again, j component. So I component, j component will always be 0 when you're looking at the curl of a vector in 2 dimensions, then plus your k component. So now our k component is going to be the partial of this with respect to x. So the partial of x with respect to x is just 1. And then minus the partial of 2x plus y with respect to y, which is also 1. And we get that. Now this part is going to change from one problem to the next. Here we get the 0 vector. So we know our curl is 0. But in general, what was I trying to get at here is that if you're doing the curl of a function of, say, a vector field in 2 dimensions, then what you always end up, remember this is M, N, and P. So what we end up with is we only end up looking at this last, ignoring that last column. So we get the partial of N with respect to X minus the partial of, this is M, the partial of M with respect to Y times K. So that's what you're going to get every single time when you're doing a vector field in 2 dimensions. And this is actually going to be important, very important to us in the next section. All right, so now what does this tell us? From what we have above, this tells us that F is conservative. So it tells us that F, the line integral over C of F dot dr is independent of path as well, but we can't, it's nice to know this right now, but there's nothing we can do with it until we find a scalar function F. So really, this is the key thing that we're using, is that F is conservative, which tells us there's a scalar function, and then from there, we'll go and we'll use this. So the vector field F is conservative. And now what we'll do is we'll find that scalar function F. That is, the vector field F is equal to the gradient of F for some function F. So now let's find that potential function. So F is equal to the gradient of some scalar function F, and our vector field F was 2x plus y, comma x, 2x plus y, comma x equals the partial of F with respect to x, comma the partial of F with respect to y. So now we can pick whichever one of these we want to. I can take, this is F sub x equals this, and F sub y equals this. I can take whichever one I want to and integrate. So I'm going to integrate, I integrate F sub y with respect to y to get our function F. F is equal to the integral of, and you can go through, this might be a good point for you to go through and try the other one to make sure that you can go through those steps independently and still come up with the correct answer. So let's say F sub y. We have to integrate that with respect to y, which is the integral of x with respect to y, and that's xy. And I was treating x as a constant, so my constant of integration can be a function of x, h of x. So now f is equal to xy plus h of x. And we've already used the information from f sub y. So now what I'm going to have to do is use the information from f sub x. So I'm going to take the partial of this with respect to x. Partial of that with respect to x. I'm going to get y plus h prime of x. But I know, but we know f sub x must be 2x plus y. So we're going to set this equal to that. So we know what 2x plus y equals y plus h prime of x. So that tells us that h prime of x, so h prime of x has to be equal to 2x. And now we integrate that, we integrate both sides of this. Thus, h of x equals, 2x squared over 2 plus a constant of integration, and this is just going to be some actual numerical constant. So plus c. And now we're going to take this, and we're going to put it in right there. Or right there, actually, is where I should put my arrow, but either one. All right, so now we have f of xy equals x times y plus x squared plus c, but you can use whatever c that you want to. And go ahead and try a c. I'm going to use 0. Try a c other than 0, and you'll see there your answer for the work is still going to come out the exact same as mine, because the c's are going to cancel regardless. What is that? X times y plus x squared, and I'm just going to use 0. So that's my f of xy. So now work by the fundamental theorem of line, well, by the definition of work first. Work is the line integral over c of f dot dr. And then by the fundamental theorem of line integrals, this is just going to be equal to f of our end point minus f of our start point. And we were ending at 4,3. And we were starting at 1, 1. So we'll take those and substitute them in. So we're going to get 12. And then plus our x squared plus 16 minus 1 plus 1. And as you had some value other than 0 for your c, you would have had that value here and then subtract it back off over here. So we just end up with 38 minus 2, so we get 36. Sorry, 28 minus 2, 26. And notice we don't know the path along which whatever we had a particle moving the object along the path C. We don't know what the path C was at all. It doesn't matter what the path C was actually. You're still going to get the same thing regardless. All right, so next let's look at what I'll do is I'll stop this video here and then we'll do another example in the next video.